Um, Another way to look at entropy today. There's so many ways, and that'll be the final one for this course. So we'll have three interpretations, or I guess maybe not interpretations. They are what they are. There is no interpretation. The equations speak for themselves. So there is no need to interpret. Okay, so let me just recap. So far, we've been considering isolated systems because this is really the way you've been taught about entropy, whether you know it or not. And when people say things like, entropy is always increasing, it's really about isolated systems because people use the word the entropy of the universe is always increasing. And so the universe is isolated as far as we know currently. Within our physics and cosmology. So we have to sort of figure out fundamentally for isolated systems what entropy is, and then we can move forward with systems that are not isolated. And so for isolated systems, i.e. the universe, we have a few definitions and expressions for the entropy. So the first one we ran across, and I'll write all of these in terms of either ds or s, depending on how we formulated them. So we saw that ds is equal to dq reversible over t, which is really just 1 over t times dq reversible, okay? And so this was the approach that this was the result we obtained from analysis of heat engines, namely the Carnot engine. And historically, this is what preceded a microscopic understanding of entropy. And the microscopic understanding is really what we discussed last time. By micro, I mean nano and molecular level and atomic level. And so when we use this approach to compute delta S, because we know delta S is a state function, and that would just be an integral of ds. Okay. From state 1, equilibrium state 1, to equilibrium state 2. And I really don't know what variables are to put in the limits here, because I've just written this as a very general integral, right? So it's just an equilibrium state 1 and equilibrium state 2. And again, here, I have to still continue this equilibrium state 1, equilibrium state 2, 1 over t dq reversible, because I don't know what form that dq reversible will take. And that will depend on the problem. And the way we find dq reversible, so according to this approach, we need to formulate an expression for dq reversible, okay? And that formulation comes from application of the first law. Okay, so this is really a very compact and succinct way to help you understand, and this is all you really need to know in terms of how to apply this equation. So you know the first law, it's pretty simple. du is equal to dq reversible plus dw reversible. And there you go. So for a given process, you apply the first law, you isolate some expression for dq reversible in terms of whatever is known about the problem, and then you can stick that dq reversible into the expression for delta S, and you can compute delta S. Okay, so this is really a mechanical or prescription for computing delta S. And here the very important caveat was that you need to have a reversible process in order to determine delta S, even though your actual process may be irreversible. Okay, so you have to construct something. Now, for the microscopic point of view, or if you have a particulate, a view of matter as particles, something that is more than just a continuum, we found last class that entropy, S now, can be written as K Boltzmann times the log of something called W, and W is just something that I use. It could be anything. You can use whatever letter you want. The letter is not important. What it represents is important. And so W is equal to the number. So it's a number, okay, of arrangements of a system consistent with a given energy U. Okay, since we're dealing with an isolated system, right, what we're going to have is a constant U, because the U doesn't change since the system is isolated. So if we were to peer down with some instrument, if we had it at the molecules and the atoms of that system, then all of the arrangements that are possible for that system consistent with that energy U is what W is. So W is just a number. And what this tells us then is that S, or to determine S, determining S boils down to a counting problem, really. So really entropy is really this, it's a counting problem, right? You just have to figure out ways to count the arrangements that are consistent with a given U. Okay, so it's that simple. Nothing more, nothing magical, nothing exotic. I'm sorry to say, it's just a counting problem. Okay, and so we saw in last class that W is context dependent, meaning that it depends on the problem. Okay, there is no one formula to use for W. Depending on what the situation is or what your particular problem is, W will have different ways to be determined. And so we saw two ways, or problem dependent, problem specific. Okay, and we saw we could get W as this n factorial over n minus m factorial for a lattice model, a very simple lattice model for the ideal gas. Okay, and if we had a polymer, well then W, where we had rigid bonds and rigid angles and only torsions, where each torsion could only take one of two conformations across the bond. So cis or trans, we saw that for a polymer, this turned out to be 2 raised to the number of torsions. Okay, and so this was this polymer that we had. A very simplistic representation. These are the torsions, and I won't draw all of them. I'll just draw a couple. Okay. And we see here that if each torsion can only have a cis or a trans, meaning across the torsion bond, you can have this kind of arrangement or this kind of arrangement, and you can flip the other one, it doesn't really matter. You see here that that's where the 2 comes from. So the 2 is because of this, okay? And then you just raise that to the power of number of torsions and you would get W. So these 2 examples give us a very clear picture of how W is context dependent. Okay, any questions so far? So based on the problem, for the next exam, you should easily be able to tell what kind of, it may not be A or B, most likely there will be another system that I will pose as a problem, but I think you should be able to critically think about how to get W. And the thing that, if you show that W is a counting thing, right? And you try to show that you're trying to count the ways, that would go a long way to indicating you understand what entropy is. Okay. In terms of a problem posed for this. And so delta S then is just computing W for the two different equilibrium states that are connected, that you're interested in, and then computing delta, the change in S. That's all there is to it. Okay. Any questions on that? Okay, great. So let's go on to a third interpretation now. This is the probabilistic interpretation, not interpretation, entropy. I'm going to call it as probability. As a probabilistic entity. Okay. And what I mean by probabilistic entity, okay, is that we saw for an isolated system, okay, for an isolated system, let's say we have this box of gas, and let's just use our lattice model picture, right? So here we have a lattice model. And if you have particles dispersed in this lattice, okay, put them here like that. And it's isolated, so we can say that it has insulation. Okay. We can ask, so this is one particular configuration. So this is just one particular configuration or arrangement of the particles, right? You could have another one, right? Here's another one. And I'm not gonna be careful about how many sites, they all have the same number of sites, okay? So just write that down in your notes. So let's see, in the same number of particles. So it's 1, 2, 3, 4, 5 particles. In this case, I could put particle 1, you know, a different distribution. 1, 2, 3, 4. Where should we put the 5? 5. Okay. So both of these systems are consistent with U. Okay. The number of lattice sites hasn't changed. The system size hasn't changed. U is the same. But these are just two different exemplary configurations of the system, right? So if you were to look at this from the big picture point of view, not worrying about the particles, you couldn't tell the difference in the system, right? Just as if you were to look at a glass of water, right? You know that all of the molecules of the water are moving around, and the molecules will be changing position over time, right? But you don't see that. All you see is this water, and to you it looks like nothing is happening, right? Yet at the microscopic level, meaning molecular level, you have a series of arrangements, many arrangements that are possible. And so this is just another one. This is just another particular configuration of the system. Okay, so that's all there is to it. One can ask, okay, very simply, and the result for the isolated system would be very simple, but when you have systems that are not isolated, things become a little bit more complicated and more interesting. But we deal with the isolated system here. And so one can ask, right, we have all, and so there's many configurations. Okay, so since n is large, m, which is the number of particles, since m, which is equal to the number of particles in the way I described the lattice model for Joule-free expansion, since m, which is equal to the number of particles, we let that go to infinity, some very large number. And in reality, this is on the order of moles, which are 10 to the 23rd particles, right, in reality. So it's a very large number. So there's a lot of configurations. Therefore, a lot of configurations, okay, at the microscopic or molecular level. So one can ask, well, what's the probability if you had the ability to peer down and capture one instant in time of the system, what's the probability of seeing any one of those many, many configurations? Right? What's the probability? So we know that there are a lot of configurations. That's W. Okay. So we figured that out. Okay. So those are the configurations that are consistent with this energy. So the question now is, what is the probability of observing any one particular configuration out of the W possible configurations? Okay, so that's the question. So does everyone understand what I've just posed as a question? Is there any? Okay. And the answer to this question is actually quite simple for an isolated system. So since the system is isolated, okay, the system is just, all of the particles are moving around, the energy is constant, there's no work being done, there's no heat interaction. And so these particles are moving around and they're exploring all of these W configurations that are possible. Okay, so they have W configurations that they can access as a group of particles, and they're freely going between those configurations, right? And just by moving, you've changed the configuration. And so if we were to say the probability of a particular configuration I, and you can call this configuration a state, a microstate. Okay? So P sub I, we can call the probability that you would observe if you were to peer down. So the question is, if you were to look and see what's the probability of finding a particular configuration, P sub I is that probability. So P sub I is the probability of a particular configuration. And the sophisticated word for particular configuration is microstate. Okay, so in the jargon of physics and statistical thermodynamics, statistical mechanics, this particular configuration of the system at the molecular and atomic level, and you can even go to the quantum level, but we will stop here. It goes all the way down. It's called a microstate. Okay, and so the probability of a particular microstate I we'll call P sub I. Okay, so this is for microstate I. It's called microstate I. Okay, and so there are W microstates that are possible for a lattice model. And so if the system is isolated, does anyone want to take a guess as to what the probability would be for any particular microstate or configuration of the system? So if you were to just, take a snapshot at a particular time and we would see some configuration of particles. Let's say the particle on the configuration on the left of the two pictures I've drawn. What would you think might be a way to express the probability of finding that configuration out of all the many?
Be 0.
Okay, why do you think it's 0? So if probability is 0, that means it doesn't exist.
Yeah.
But what I'm saying is that this is something that exists.
Well, I was just I thought it was 0 because I was thinking about the probability function of a continuous function needing to be normalized density function. So I thought about how you would make that expression, the Boltzmann expression, equal to 1. And then if you evaluated the integral, the probability of being at one particular state would just not exist because it's continuous.
Ah, okay. uh, you've you've jumped way ahead. Okay. I appreciate that you've done that. So this is actually even much simpler than that. So we will get to Boltzmann weights a little later. At this point, they're not really that, we don't really need to invoke a Boltzmann weight. We could, but sort of, let's think about it another way. And these are discrete. So the way I've described this is as a discrete function. To look at continuous systems, and you're right, in reality, these are continuous systems. The mathematics becomes very, very, now you're going to deal with multiple integrals, multidimensional integrals, integrals that are on the order of 10 to the 23rd dimensions. So that's why I have not dealt with continuous systems. Okay, this is all in the realm of statistical mechanics and for a graduate level course. But you're absolutely right. These are continuous systems, and out of this, we would get something that's akin to a Boltzmann factor. But right now, for this discrete system, okay, what do you think it would be? Forget about normalizing. Forget about anything like that. Just keep it very simple. So if you have W configurations and the system is isolated, and I'll tell you that there's nothing preventing the system or the particles from going from one state to another, from one microstate to another, or from one configuration to another. Because the system is isolated, there's, you know, the particles just keep moving freely. And so we've kind of bound the number of configurations they can move between as W. So does that help?
1 over W.
Ah, okay. 1 over W. That's exactly right. So the probability of any one of these configurations or microstates is just 1 over W because they're all equal. There's nothing preventing or favoring one configuration from another because the system is just isolated and there are no internal barriers. They're just moving around. Okay. And the thing, you can seek recourse to the container of gas molecules that would be isolated, the Joule-free expansion, the initial state that started all of this, right? That gas container, you know, there's nothing preventing the molecules from exploring all of these W states. And that W actually, yeah, I've shown this to you in the discrete form, just for simplicity. You're absolutely right, Sheldon, that this would have to be a continuous, this discussion has to be rigorously continuous using integrals, but that really becomes a bit more complicated and you have to have a little bit more mathematical machinery to do that. So I haven't done it. Right, so the probability of one of these microstates is equal to 1 over W. And that's exactly right. Okay. And so this idea of normalization, I'm going to, just to satisfy you, I'm going to say that this is normalized. Okay. So for any one of these states, we know that the probability is 1 over W. So if you want to normalize it, so let's just normalize it. If you want to normalize the PDF, which is the probability distribution function or the probability density function. How would we normalize it? Well, normalization means that all of the probabilities sum of p sub I must equal 1, as Sheldon pointed out, because all of the probabilities have to add up to 1. Okay. So in this case, we have W microstates, right? Because this p sub I is the probability of a particular microstate, just one of the W. So our normalization, let's see, would be a sum where I is going to run from 1 to W, okay? Because we have W microstates and we just sum p sub I, okay? But this is going to be the sum where I goes from 1 to W. P sub I, we've just found out, is 1 over W. And 1 over W is a constant, because W is a constant. W doesn't change in this very special case of an isolated system. So what we would have is a constant, and really you can think about it this way. I'm going to make this very explicit. It may be too much for, maybe it's overkill, but I'll write it this way. This is going to be a constant 1 over W times 1. Okay, so we can pull out a constant in a summation. If you have a sum of terms and each term has some constant, we can just pull it out. So that just becomes 1 over W times the sum I is equal to 1 to W of 1. But if we sum 1 W times, so we have 1 plus 1 plus 1 plus 1 plus 1, and we have W terms, that summation is just going to equal
W.
W. So that means we have 1 over W, which is this guy, and the summation is going to give us W, and 1 over W times W is 1. So indeed, when we sum over all of the probabilities over all of the microstates that are available, if the P sub I, the probability of a particular microstate, is 1 over W in an isolated system, which it is, the distribution is normalized. It equals 1. So we don't have to worry about the normalization. Okay, Sheldon? So that, even in this discrete case, everything works out. Okay, so with that being said, we have the probability of a particular microstate I. The question I want to ask now, okay, now that we have this result, okay, is what's the average? So the next question, what is the average value of natural log P sub I? Okay, so what's the average value of the log of P sub I? And again, if W is very large, you can see that P sub I is going to be kind of small, right? If W is on the order of, 10 to the 23rd, or sorry, or some very large number, it would not be 10 to the 23rd, it would be 23 or maybe 100 or something like that. P sub I would be very small, but if you take the log of it, and of course, if you would negate it, you might get something that's like an integer that you can deal with. Okay? Much as we did for W by using logs, we can apply the same for P sub I, which is just the inverse. Because in one case, you're dealing with very large numbers, in the other case, you're dealing with small numbers. So if you take logs of these things, you get some numbers that are palpable, they're not outrageously big or small. So you could ask, what's the average value of log of P sub I? Okay, and the way we compute averages, once you have a probability distribution function, and this is what you've done all along when you've used the expressions for obtaining averages, let's say in an experiment or something like that, the way you get an average value, and I'll label this with a bar. Okay, so this indicates an average of log of pi. Okay, is you take a sum where I goes from 1 to W, okay, of the probability of a particular state, right? Because log of P sub I is really the log of a probability of a particular microstate. And so we want to sum up this, we want to get the average by summing up over all the states, or by considering log of pi for each one of these states. So the way we would have to start considering this is that we would probably have a summation over all of the microstates. So we can start out by writing a summation where I runs from 1 to W, where W is the number of microstates in total. And we would have this product of the probability of finding that microstate, that microstate I, which is P sub I, times the natural log of that probability, which is what we're after. And so this is a general definition of how we compute averages. Okay, so this is the general definition of how we compute averages. So you know, in the past, what you've been told is that, okay, let's say you have, let's say you have T experimental data, right? So T is the number of experimental data that you may have, right? What you would do, right, is you would, and let's say T is equal to 5, right? What you would do is you would, to compute the average of T, right? You would say you would take T1 plus T2 plus T3 plus T4 plus T5, and then you would divide by 5, right? That would give you the average. Is that foreign to anyone? Right. So if you had T values of some experiment, so you have T experimental data points, and if let's say T is 5, and if you wanted to get the average, you would just sum them all and divide it by 5. But really what you can think of this as, right, is a sum where I is equal to, well, let me not go to the sum yet. This is really just 1/5 times T1 plus 1/5 times T2 plus 1/5 times T3 plus 1/5 times T4 plus 1/5 times T5. Okay. And it turns out then that 1/5, since we have 5 data points, and we're not going to weight anyone any differently, meaning that no 1 or 2 or 3 or 4 of these particular data points is going to give in any more weight than all of the others. They're all equal weight. Okay, so each one counts 1/5 in the average, just like when you take your average for your grade for a course, right? In this case, we have different weightings for the exams, the homework, and the midterms in the final. But if they were all equal, right, and let's say we had 5 things in the course, 3 exams and 2 homeworks, let's say, for instance, right, they would all be given an equal weight, 1/5. And so when you computed your average, you would just sum up the value, your grades on all 5 and divide by 5. But if you had different weights, the final may be 50%, then you would have to use 50% for that weight, and then everything else would have a different weight. But all of the weights would add up to 1. And in this case, all of the weights do add up to 1 because 5 times 1/5 is 1. So the probability of any given state is 1/5. And so the average then, T bar, is just the sum where you have T running from 1 to 5, the probability of T times, in this case, since we're only after the average of T, it's just T there, right? So you have this product. So this gives us the average of T. And so this is the expression you've always used. This is the way to think about averages, because averages come from probability distribution functions. And so when you talk about an average, you always have to keep in mind, and you always have to bring along with it in your brain, in your mind, a probability distribution function. And in this case, it's given by this. So by analogy, we see here then, to get the average value of natural log P sub I for these microstates, we have to have a summation over all the possible microstates. The W would correspond to 5 in the case of the T experimental data points. And the log P sub I would correspond to T in our example of the T data, the values of the data. Okay, so this is the expression we have now to get the average value of log P of I. And if you want, I can put brackets to indicate that this is a product. And we're taking the sum of a product. And I can do that here too. So it's the sum of a product. We'll see this again in quantum mechanics. Quantum mechanics is all about averages because it's probabilistic. And so this form, right, if you remember this, everything will be very, very simple. It's just that the equations become a little bit more complex. The functions become a little bit more complex, but the concept is very, very simple. This is the concept. It's so simple, it's almost trivial. Okay, so if you want to compute the log, the average of the log of p sub I, we can do this using this expression, okay? So the average value of the log of p sub I is equal to, what is this? Sum I is equal to 1 to W p sub I times natural log of p sub I. Okay. So let's see, what is p sub I? P sub I is just W, 1 over W, so this becomes I equals 1 to W, 1 over W, and we know that this 1 over W is a constant, and then in here we have 1 over W. Okay? Is everyone okay with that? Now, since 1 over W is a constant, right, we can take it outside. Actually, what we can do, what we'll do is write, with log of 1 over W is also a constant because 1 over W is a constant. So what we'll do is we'll take that out, and then we'll keep the summation I is equal to 1 to W of 1 over W. Okay, is everyone okay with that? Now, what is I, the summation I equals 1 to W of 1 over W? What does that lead to? What
I
do you
guess
know?
it looks
Go ahead.
looks like a harmonic series. So 1 over it looks like it diverges to infinity.
Well, so what is 1 over W? What have we defined 1 over W as?
Oh, the probability of any state.
Right. And so if I sum over W all of the microstates, the probabilities, what numerical value must that be?
1.
Yes, that's 1, right? We just, let's see, we showed that up here. There. Right, it's normalized. So what, okay? Is that okay? So this guy just turns out to be 1. And so then our average of P sub I is equal to natural log 1 over W. And of course, that's going to give us 1 over, that's just going to give us what we thought it would be, right? Because the log of P sub I, they're all the same because all of the P sub I's are the same, okay? So this should not be surprising that we got this, okay? So the average value, if all of the numbers are the same, right? We said P sub I is just 1 over W. So for all of the states, it's the same. P sub I is the same. So it's like adding, you know, if you had 5 data points and each data point was 10, right? 10 plus 10 plus 10 plus 10 plus 10 divided by 5, you're going to get 10. That's your average. But the thing is that we get some insight here. Okay. So log of P sub I, okay, which is the result of this summation, okay. So that summation, which is equal to this guy here, so we can write this as I is equal to 1 to W P sub I natural log P sub I, okay, and all of this is summed, and that's equal to natural log P sub I. Everyone okay with that, the way I wrote it? Because all I did was say, all right, well, the average value, this guy, is equal to this thing in the box. And that thing in the box is just equal to log of P sub I. And so that's what I've written here. Okay. But natural log of p sub I is 1 over w, which I can write as natural log of w to the minus 1. And now I'm going to bring that minus 1 down, which is equal to minus natural log of w. Right, so all I did was bring the exponent down in front, so I get minus log of w. And all of this on this side is equal to I is equal to 1 to w, sum of p sub I natural log of p sub I. And that gives us this expression right here. Okay. But what is natural log of w? Because recall, S is equal to KB natural log W. So log of W is S over KB. So we can say I equal 1 to W. The summation of this product of P sub I natural log of P sub I is equal to log of W, which is equal to S over K sub B. And it's the negative, because I have minus log W. So minus log W is equal to minus S over KB. So this is minus S over KB here, right over here. All right, and so now what I'm going to do is just solve for S, because I have S over KB here, or minus S over KB here, and I have this expression over here, and all I have to do is solve for S. And what I get for S then is equal to minus KB times this summation, I is equal to 1 to the number of microstates that are available of the product, the probability of a microstate I, times the natural log of that probability. And lo and behold, we have another expression now for what entropy is. And this is the probabilistic result of what entropy is. No chaos, no disorder, but probability. And it's very obvious that entropy is associated with probability, because the only thing apart from a constant, K sub B, that appears in this expression, which is the discrete analog of a continuous form, you would see this also in a continuous form, but that summation would now have a multidimensional integral. That's why I have opted not to use that approach here. But apart from a constant and the summation sign, the only thing here that you see are probabilities. That's all you see. I mean, that's it. It's that simple. Nothing else, nothing more, nothing complicated. So entropy then turns out to be something that's related directly to probabilities. And in this case, for an isolated system, it's related to the probabilities of observing any particular microscopic arrangement that is a microstate that is available to a system under the conditions in which it exists. So the macroscopic conditions of temperature, volume, and its internal energy, making sure that we understand that this is for an isolated system. Okay. So this is pretty amazing. So now we have three understandings of what entropy is. So once we are given a set of probabilities for a system in terms of its microstates, okay, and one can approximate these probabilities. So for instance, in the case of a polymer, we know that, okay, let's say each torsion can take two states, right? We know that the probabilities of each microstate, let's just say there's one torsion, we know the probabilities. They're just 1/2, right? So does that make sense? Right. Okay. So anyway, it's getting late, so I'm going to stop here. But this discussion I hope everyone followed. It's the third way we'll consider entropy, and it's the probabilistic view of entropy. So any questions or comments? Again, P sub I is the probability of observing a particular microstate. All of the P sub i's represent a probability distribution function, which is normalized. We just showed that in this class, so we don't have to worry about it being a funky probability distribution function. It naturally comes out to be normalized. So it's a proper probability distribution function. Okay, any comments? Okay. All right. Well, I hope this is insightful. I think the last few lectures and up to now, including today, are probably, I think, some of the coolest lectures of this class because they illuminate what entropy is in a very precise way, using very precise equations. The only thing I have to apologize for is that in the case of continuous systems, which in reality everything is continuous, we really would have to use integral approach. The integral, the summation would be replaced with integrals that are of higher order dimensions. But I think this proves the point and allows us to see the concept very clearly and very directly without confusion. Okay, I'm gonna wish everyone a great weekend. If there are no questions, I will open the floor one last time for questions, if there are any. Okay, I wish everyone a safe weekend and I will see you Monday. Thanks for your participation, everyone.
Thank you.
Thank you.
Have a great weekend.
You too, thank you.